Okay, so as we already discussed in the last week, that today I'm going to present, like I'm going to talk about, like in I can better it's better to tell that it's an introduction of polarizable force field. Deepika already introduced about the reactive force field, so it's better to introduce this another type of force field, which is called the polarizable force field. So as you know that in empirical force field and molecular dynamics, empirical force field is widely used in like for biological systems and for chemistry, biological system, and like material studies. Okay, so this type of studies, the accuracy of this type of studies is typically based on the how the utilization of this potential energy function, how you determine your potential energy function. So in general, this potential energy function you can determine in normal classical force field as like suppose R, you can determine as some bonded term and reverse term and some electronic interaction term. So broadly, you can write your potential energy, classical potential energy function like some bonded term, van der Waals term, and electronic term. So this bonded term also contain like typical tool the bond angle and torsional angle, and this van der Waals is taken care with the help of Lennard-Jones potential. And this electronic term, which I mainly focused here, this is electronic term is just basically you can consider index suppose okay. So with this Coulomb interaction, so the why we need the first we will encounter that why we need polarizable force field. So if you see, so this is the classical normal rigid force field. So in this type of rigid force field, the one of the major limitation is this like the way the charge distribution of the molecule is treated. So typically in effective partial fixed charge are assigned for each and every atom type of which is the independent of the environment in a classical rigid force field. So which are adjusted to account the influence of induced polarization in very average way. So there is the inability of the charge distribution to vary and adapt as a function of the local electric field. Okay, so it's considered as a major limitation. So the major limitation is based on the charge distribution assignment in your force field. So this type of assignment they've done in like the normal force field like amber or PLS, this type of force field. So when we need to calculate, like when you need to calculate or when you need to account the intermolecular interaction between the atoms, so then this type of force field doesn't work very well because they didn't capture the local electric field effect or the environment effect. Okay, so to capture this intermolecular interaction correctly, okay, in a variety of environments, so you need polarizable force field. So, so in from this point of view, it's become clear that the inclusion of electronic polarization it's crucial for a next generation of force field. You can tell for the next generation of force field. Okay, so it depends like what is your point of interest, like what type of study you want to do. So it depends. So which force field is better, like polarizable force field you need or not? Only the rigid force field can able to do the job. So this is your point of interest. But this polarizable force field, you can give, is the basis of this force field. You can tell, like as you all know, that dipole, electric dipole, is the linearly proportional to the local electric field. Okay, so from the, like you can tell, the from the environment is induced in the molecule. So if the electric field is not too large, so there is a condition that if the electric field is not too large, so then you can write that's the induced dipole of that system mu is proportional to that electric field, and here the proportionality constant is the alpha. So we're familiar with this type of equation. There is a mu equal to alpha into E. So mu is a induced dipole and of a particular atom, and E is your total electric field. So this total electric field is generated from the uh, permanent atomic charge assigned for each and every atom and the contribution of the other induced dipole. So we can further, okay, so I'll discuss this later. So this is the most fundamental equation, that the induced dipole equal to polarizability times alpha is your atomic polarizability, right? Like alpha is your atomic polarizability, mu is your induced dipole, and E is your total electric field. Is your total electric field. So this total electric field is how this total electric field you can consider. So that we'll discuss. So in this, this is the need of polarizable force field, because we need to encounter, like I repeat, that we need, when you need to encounter this, when you need to treat this intermolecular interaction in a variety of environments, so then we need this type of polarizable force field. So to calculate or to make this polarizable force field, there are few methodologies. Okay, so the first, we can say there are three methodologies. One is induced dipole model. The second one is classical two-door oscillator model, and the third one is fluctuating charge model. So these are the methodologies like commonly you can use to for the basis of polarizable force field. So I'll explain one by one. So first I will start with this induced dipole model. So what is induced dipole model? So in this induced dipole model, the basic idea of this induced dipole model comes in the year of 1917 or the paper of Silverstein. So after that, the like modern implementation of this type of model in your MD simulation is based on this 1972 paper of Appelquist, and this Appelquist method is later modified by Betty Thole in the year of 1981. So that's the history of this induced dipole model. So this induced dipole model is first, like this type of model is first encountered by Professor Silverstein. So I guess this is Gary Silverstein. In 1917, and later by Professor Appelquist. then modified by okay. So I'll discuss like how induced dipole model work. So if you have any question, you can ask. So any question, or if I'm saying anything wrongly, so Vamshida or others can correct me. After
Yeah,
this,
Subhajit,
okay. Yeah.
just one comment. So,
Hmm.
in the very beginning of your lecture, you said
Hmm.
the our motive is to find the form of the potential energy or function.
Hmm.
So, I think the form of function is well known, but motive is to find the correct potential energy surface,
Hmm.
not the form of potential energy function. Because I think form of potential energy function is well known that it contains all those terms,
Hmm.
but how our model is capturing the potential energy surface correctly or not, that is our motive.
Okay. So the what uh, I am talking that is there is a this potential energy function is well known. So in the rigid force field, so they capture this electronic part like this Coulomb interaction. So they assign this fixed partial charge for this every atom. Okay. So, but
Right.
like we're going to discuss that in the polarizable force field, basically this electronic part they didn't model like this type of Coulombic interaction portion. So they modeled it differently. Okay, so that eventually include this electronic polarization effect in your force field. So this is I'm uh, trying to
Okay.
tell.
Okay.
Okay.
Mm, okay.
And
So,
Subhajit and Adobe. And hello.
Yeah.
Yes.
Yeah. Subhajit,
Yeah, I think so. The potential energy function is well known. It is not true. So we don't know the potential energy function of this system, right? So we are all these are approximation.
We
So we
we
are just
model
trying
as
to mod.
potential energy
Yes,
function
yes,
with various.
yes. We're just trying to model our system with different forms.
Yes. So in this polarizable force field modeling, we
so
only
Subhajit,
Hmm,
just one
hmm,
thing. So
hmm,
basically, the Silverstein model and Applequist's work, and then later on BT whole work. So
hmm.
basically, they have done the work in the calculation of accurate this alpha value, right?
Yes.
Considering the electric field to be weak in the
Yes. Yes. Yes.
in that approximation.
In
Oh,
that
okay,
approximation.
okay, okay, Subhajit.
So so in this what I am talking like they have for the calculation of for the consideration of electronic polarization, they have only encountered this electrostatic interaction like you electrostatic this portion only. Okay. So am I clear?
Yes, yes, Subhajit.
Okay. So now I'm going to discuss like how this induced dipole model works. Okay. So the first for this modeling, they have considered like suppose your system have n different atom. So they have considered the arrangement of n different atom which has a polarizability. Okay. So now they calculate the induced dipole moment. Okay, so for the induced dipole moment, I already told that's a simple equation. This is induced dipole moment is equal to polarizability times electric field. So how they model this electric field or how they calculate? So in this regards, we can write that this suppose the atom index is P or Q is the atom index. So we can write the dipole moment or induced dipole moment of the atom P. You can write as so in this equation, this is the simple mu into alpha into E. So here I expand this E as a EP minus some term. Okay, so I'll discuss like what one by one. So this is TPQ. So this TPQ is your, so alpha, you know, that's the atomic polarizability tensor of this particular atom index P, and mu q is your induced dipole moment of another molecule. Okay, that is qth molecule. And what is TPQ? So TPQ is your dipole field tensor. Okay, so now so there in this context of this total electric field, so if you look closely, so they will encounter both things. Like one, they have encountered this electric field with for this assignment of this permanent charge of every atom. So this is this one, and the another one is this is with this help of this interaction tensor with this other induced dipole. Okay, so how they can calculate this dipole in field tensor? This nice form of the dipole field tensor. So this TPQ, we can write it as five. So this is the form of dipole field tensor. So what is RPQ? So RPQ, as we all know, that RPQ is the distance between atom P and Q. What is XYZ? XYZ is a Cartesian component of like the vector connecting between the atom P and Q. So this is the Cartesian component of okay, so we can mark this equation as equation 1. This equation is equation 2. Okay. So now what I do? Hello.
Subhajit. Yeah, so I have a couple of questions here, a couple of doubts. So first term in the TPQ term, so 1 upon RPQ cubed, right? So this is the dipole-dipole interaction term, I think. The third cube term is the dipole-dipole interaction term, right?
This is
I don't know, but I think, yeah, this is the unit matrix. And the second 1 upon RPQ to the power minus to the power 5. So this is the induced dipole interaction term, right?
Yes, this is the dipole-dipole, and this is the dipole-induced dipole.
Induced dipole interaction term. So then in the equation 1, we are subtracting these dipole tensor times induced dipole of other atoms. So why we are subtracting this?
Okay, so in this equation 1, so can you repeat like why subtracting this?
Why mu p equal to alpha p times ep? This is the induced dipole on the p atom.
P atom.
And then we are subtracting all those components coming from the other atoms, like, right?
Yes.
All those. So here we are subtracting this. Okay. Okay, you can carry on.
So
actually, I have a doubt in equation 1.
Yes.
So this alpha p, you said this is a polarizable tensor. Is it rank 1 tensor, or like there is only one index?
Okay, so with respect to time, it's a tensor, but without making any time, you can consider it's as a like if there is a n atom, so you can consider it's a n by n matrix. The sorry, it's a 3n by 3n matrix. Okay, so this is the n by n
No,
matrix.
actually, I'm talking about this alpha p.
Alpha, no?
It's polarized. Yeah.
So it's a 3 by 3 matrix for individual atom. Okay, so if there is a p atom, so there's a 3 by 3 matrix. Okay, so the matrix component of alpha xx, like alpha xy, alpha xz. So that's a 3 by 3 matrix. Okay. Okay, so we can write this equation 1. Okay, so after rearranging, we can write this equation 1 as so just I will rearrange this equation 1. Okay, so nothing else. So after rearranging this equation 1, we can write the generalized. We can write this equation as a single matrix equation. So writing this equation as a single matrix equation, we can write this as a mu equal to E. This is equation 3. So what's the form of A here? The form of A is very simple. If you consider this equation, there's a form of A. It's basically your inverse to inverse, and there's the diagonal elements, and the off diagonal elements should be T1 to T1n, and here after element should be Tn. So it's a form of this A matrix. So just simply write this equation in a simple matrix equation. Okay. So now what they did, so they did take this inverse of this matrix. So which is a B matrix. So B matrix is basically the inverse of this A matrix. So the B matrix, the form of B matrix, you can they write this form of B matrix. These notations are important. They write this B matrix as a partition matrix here, 3 by 3 element. So it's B1, 1, 1, 2, this up to B1n, and the column there is Bn1. So from this equation 3, so you can write this form of B as a 4. So from this equation 3, equation 3 is A mu equal to E. So from this equation, we can write that mu equal to P into E. So because B is a inverse, so we can write mu as a B into E. So these are the matrix. Okay, so again, if I convert this matrix as a n matrix equation, so you can write it as a equivalent to in matrix equation. So then you can write like the atomic index is suppose P. So mu P equal to summation over n P EQ into EQ. You can write. Okay, so now we can consider that this electric field, this E, is uniform electric field for this every molecule. So we give a uniform electric field. So we can take this EQ as E for all Q. So then you can simply write this mu P as your into E. Okay. So now you can able to see, so if we simply write this equation like this, so then this equation is simply look like our very first equation. This is equal to alpha into E. So from this equation, you can calculate this total dipole moment induced, like how much the total dipole moment induced, the total the molecule is basically suppose mu mole molecular. So then you can add it up for the index. And you can write P. So then you can add another index into E. If you see this equation, so this equation is very much similar to this equation equal to alpha into E. So this portion, so this summation is basically your alpha molecular. So this is your molecular polarizability tensor. So after diagonalizing this alpha mole, you can able to get this the three components of this polarizability. But here,
Subhajit, sorry for interruption. So in the equation mu p. So when mu p equal to sum over q equal to 1 to n bpq and eq, right? Then you are writing eq equal to e for all q. Okay.
So this is assume that the electric field is uniform for every q.
Okay, that's fine.
So by diagonalizing this alpha molecular, so you can able to get these three components of molecular polarizability. Okay, so now in general, this you need this for this calculation. You need this whole B matrix. So the calculation is B matrix is not computationally cheaper. So in molecular dynamics, they use like iterative procedure. Okay, so that's the story of another day. Like in Tinker, they have used iterative, like any type of molecular dynamics, they used iterative procedure to solve these equations. Okay, so this is a method proposed by Applequist, but there are few problems. Okay, so this problem itself deserves one class. That's in the case of like diatomic molecules. Okay, so if you consider these isotropic polarizabilities of each atom, like HCl. So if you consider this isotropic polarizability for hydrogen, and if you consider this isotropic polarizabilities for chlorine. So as you know that towards this bond axis, we can consider this polarizability in two ways. One is the perpendicular way, and another is the parallel way. But there are few problems. There are at least two, not few. That there is a one major problem. The problem is suppose the molecule is HCl. So if you consider this isotropic polarizability of hydrogen as alpha H and the isotropic polarizability chlorine as alpha Cl. So this parallel and perpendicular there are two components of polarizability. There is a parallel and perpendicular component of polarizability with respect to this bond axis. You can write as is the additive term of the polarizability for the molecule, and with this additive term divided by this is your perpendicular one, and your parallel one is so this is parallel term, parallel polarizability of the molecule. So from these equations, so we can able to illustrate some features that see we can predict that if we consider the isotropic polarizability of molecule. Okay, so but this alpha perpendicular and alpha parallel gives you the anisotropic behavior or anisotropic polarizability of molecule. Although you consider this the polarizability is atomic polarizability is isotropic. So this is one conclusion, and the next conclusion is the parallel molecular polarizability towards this bond axis is generally greater than the perpendicular. This alpha parallel is generally greater than alpha perpendicular, so that you can measure. And like one more thing, that's if you see,
So
Sumit, when
so you this alpha perpendicular and alpha parallel,
parallel,
how you define it? Actually, I just missed, if I'm not wrong. I just missed
okay,
that.
so this alpha H and alpha Cl is your isotropic atomic polarizability. So they define the isotropic atomic polarizability of
Yeah,
each atom. Okay,
yeah, that.
so without taking this additive for the molecular polarizability, so there's a form they have used that for this perpendicular polarizability and parallel polarizability towards the bond axis. So this is the form. So the derivation I don't know.
So
Okay,
okay. So alpha perpendicular is basically it's perpendicular to the HCl bond.
Bond axis,
Right.
yes. Perpendicular polarizability.
So alpha is your you said this, it is a tensor. Huh? So
yes.
yeah. So how this component of alpha perpendicular will be a component of those tensor? Okay. So how it will be defined if you are taking alpha perpendicular for so and then so there will be some components 0 in alpha perpendicular tensor.
Because alpha perpendicular tensor.
So this alpha perpendicular will have its own tensor form, and then alpha parallel will have its own tensor form. Okay. Yeah.
No, alpha, I want to say here that alpha has a matrix form. Okay. So for HCl, it has alpha, total alpha. Alpha has different components. Okay. HCl, this is not a scalar value.
Yes.
Okay. Then we can represent this matrix in different frame of reference. Means we can transform matrix transformation. Vector transformation means you need to define the rotational matrix and this vector form, and then multiply with this rotation matrix. Okay. In similar way, you can transform this whole matrix into another frame of reference by using this Q transpose Q inverse vector into Q, like that, like similarity transformation. I think this kind of thing, this kind of transformation, from this kind of transformation, you can arrive this kind of this alpha perpendicular means along this perpendicular, what is the component along this perpendicular basis and what is the component along this parallel basis of that bond. I think.
So this type of transformation, if I'm not wrong, so this type of transformation they've used in this velocity paper, no? So this,
yeah, velocity. Sorry, what are you
this
telling?
velocity SFG paper.
Mm-hmm.
They have used
Velocity.
this type of transformation.
Yeah, there is the B matrix. Yeah. From rotational matrix. From rotational. Yeah. From one frame of reference to another frame of reference.
Another frame of reference. So they have used this type of transformation. So I can give you, Vangsuda, I can give you the link.
Yeah. Okay, Subhajit, you share that link.
So they have
Subhajit, but I have one very basic question. You have written that alpha parallel is greater than alpha perpendicular. But if I see the form of equations, in alpha perpendicular you are adding
one more
some term.
Adding some more terms.
No, actually, I was seeing that determinant, this denominator was same, and what numerator you were adding. Yes. Okay, now it's fine.
I just copy paste from the app. So, any more? Okay. So there is one problem, like if you see these equations closely, so then like when this R, so the distance between these two molecules, so when R is approaching towards this value, like 4 alpha C to the power 1/6. So then you can encounter this alpha parallel is going towards this infinity. So this is a major problem of this Applequist model, that this happens because of this cooperative interaction. They use this term in Applequist, use this term that, like this cooperative interaction and like head-tail interaction between two induced dipoles. Okay, so in the direction of bond. So this is not the Applequist exactly is this word, that this becomes infinity. This alpha parallel becomes infinity when R approaches towards this value, like 4 alpha H alpha C to the power 1/6. So this is mentioned that this is because of head-to-tail interaction between induced dipoles in the direction of bond. So this is the main problem. So this problem is later this problem solved by this Professor Petitol in the year of 1981. So this is how this induced dipole model works. Okay, so
Subhajit, so last line, can you explain by showing some schematic or picture or cartoon like this? I didn't understand that correctly.
Okay, so when this in this dipole and induced dipole model, like every atom they are considered as a dipole. Okay, so in this dipole, so when R becomes very small, so when suppose this head-to-tail interaction, so if we consider this type of interaction, so then this alpha parallel becomes infinity. So it becomes infinity. You can able to see from this equation also. So these type of interaction, like they have used, the quiz use the term like head-to-tail interaction. So towards this bond direction is able to make this
Okay, so
polarizability
head to tail.
infinity.
So head to tail interaction between two
dipoles.
Atomic induced dipoles.
Atomic induced dipoles. Yes.
Okay, then it's fine.
Okay, so these problems solved by Bretithol in the year of 1981. Okay, so this is the basic idea. So today, as I told, today is the introduction, okay, of this polarizable force field. So this is the basic idea they have used for this inclusion of electronic polarization with the help of induced dipole model. So now, like
Subhajit, that Subhadip's question, that actually better understand in terms of that interaction energy in terms of induced dipole, means in the interaction energy will diverge if there is very short range closeness like this arrangement head to tail. So this kind of divergence actually, if we consider this point dipole, they are, if those two point dipoles are far apart, then this approximation is okay. But if they are close and close enough, then they are starting to see electrons of each other. Means in terms of the interaction energy, in terms of dipole, I think induced dipole, this would be better visualized. This kind of singularities. Okay, just one comment. Okay.
Subhajit, can you go at the last when you have said that R tend to something? So I think this force should not be there.
So now I will discuss about the second methodology, which is a classical Drude oscillator methodology. So this methodology is developed by how much time we have?
Okay, so ideally you have 15 minutes, 15? But you can go ahead, I think. Yeah, 15.
Okay, so if 15, okay, so how much? Okay, so classical Drude oscillator model. So this is developed by, like, the early work is done by Professor Paul Drude in 1902. So he has developed this to as a simple way to describe these dispersive properties of bacteria. Like how I'm going to introduce this only in the philosophical way, how this Drude oscillator model incorporates this electronic polarization. So to represent this electronic polarization, so they have introduced a massless charged particle, which is attached to the atomic center of each polarizable atom. So suppose there is water and with this oxygen as well as hydrogen. So they considered a massless charged particle which is attached with this oxygen and hydrogen with a harmonic spring. So, and then after this consideration, they, like, self-consistently they find this the position of these particles, like the massless particle, or you can say the Drude particle, or they adjust its position with this self-consistent by calculation to finding the local minimum of the system of the atoms in the system. Okay, so in this model, this polarization is determined by a pair of point charge. Okay, so separated by variable, separated by a distance d. So in the given atom, okay, so suppose in the given atom, they assign the charge q. Q is the charge assigned for the atom, and they have assigned another charge QD for your charge assigned for root particle. Okay, so after this, and D is the distance between this root oscillator and this atom. So after assigning this Q charge of this atom, and QB is a root for the root particle, so they adjust this the charge of the atom. Okay, so it's replaced by in place of Q, they have replaced by Q minus QD to preserve the net charge of the atom to the oscillator fields. So at first they have assigned it's a Q, and after that they have adjusted it with a Q minus QD to preserve the net charge of this auxiliary particle, like the root oscillator, and this your original particle. Okay, so and here you can consider KD is your the force constant of this harmonic spring. Okay, so now in the MD simulation, in the absence of electric field, the root particles oscillates around position R. Okay, and in this case, like when the presence, if you in the MD simulation, if you applied a uniform electric field, so then the root particles oscillates, it is displaced from its position, and the position becomes R plus D. You can consider. So there, this D. Okay, so this displacement D, they have this root separation. So this is called root separation. Is related to your this force constant Kd and the electric field that we apply, and obviously your charge of this root particle. So this root separation D is your QD. And for this case, the formula for this induced atomic dipole, so mu I already introduced, this mu is your induced atomic dipole, becomes okay. So this expression, so this is your induced dipole, and this expression simply give you the isotropic atomic polarizability alpha, which is you can basically express in terms of this everything in terms of this root oscillator. So QD is basically I introduced, there is a charge assigned for this root particle, and KD is your force constant. So you can assign your polarizability in terms of this QD square by KD. Okay, so this is a very simple, like very basic or brief idea of this root oscillator. So I repeat, there is just a consideration of massless particle, which is called root particle, which is attached with every atom, with a harmonic spring. So from that consideration, you can able to calculate your atomic polarizability. So now, like as a computational chemist, like one question comes in everyone's minds: this polarizability calculation. So we already encountered two types of polarizability calculation. One is induced dipole moment, and the another is root oscillator model. So we can consider this root oscillator calculation, is it computationally feasible or computationally cheaper than this dipole interaction calculation? But in this regards, the answer is no. Okay, so as you know that we for this root oscillator calculation, we don't need to calculate this big Tij, this type of Tij tensor. We don't need to calculate. But this benefit that's not calculating this Tij, so this benefit is balanced by this extra charge calculation, because with the every atom you add a root particle. So this is the charge calculation becomes significantly large. So this significant computational, so this is not computationally so cheaper than this dipole-dipole interaction. So to make it cheaper, so one can assume that the root particle only attaches to the non-hydrogen atoms. Okay, so because this non-hydrogen atoms dominates this molecular polarizability. So there are can give you. So I don't know much about this root oscillator. So there are two models. Okay, so in encounter there are two models for which applies this root oscillator concept. So one model is SWM4DP, like your T4P model. So the full form is, this is a simple butter model. 4 is your 4 points. The root oscillator concept I found like they're more or less similar with your T4P concept. So with root polarizability. Okay, so this is developed I think in the year of 2003, and the later with the corrections. So they, the same group developed another model, water model, that is NDP. So N, the whole thing is same. N is because of negative. So this are developed in the year of 2006. Okay, so the concept is same like this water, hydrogen. So there is a charge for hydrogen also, and they have just considered a root particle in the vicinity of oxygen. So, and they have also assigned negative charge for this root particle. Okay, so this is the basic concept of root oscillator. But as I already told, this root oscillator is not so computationally cheap like your induced dipole moment polarizability calculations. Okay, so now it's time for the last one. There's a fluctuating charge model. Okay, so
Yeah, Subhajit,
yes,
just before you start the third one, so I have one simple thing. So this
yeah.
root particle, the root particle is same, like it's unique, same for every atom, like everywhere in the in your simulation box you are assigning same type of root particle. Okay, and it's massless. So my question is
Mass,
how.
it's massless, and
So
your question is.
my question is how it is capturing this local environment, like you are, this is same, root particle is same, and then your electric is also uniform. So if you go to your expression where you have written, just scroll up here, so your QD is same.
Same for like same type of atom. Okay, so not for
Same type of atom. So
for
what I am
oxygen it's
asking is,
same, for every oxygen it's same, for every hydrogen
yes, for
it's same.
right, it's like similar to this your rigid water model. So they have fixed assigned charges. So the question is how, or like which term is capturing this local environment, because for every different environment, so your polarizability or this induced dipole moment, those quantities should be different. So only term I see is this force constant.
It's K.
But yes, but I'm not getting how it's.
I think in my suggestion, this KD will depend upon the actually environment. So this value will vary depending on the environment. QD will be fixed for a certain, for a specific atom, but KD I think it will vary.
How? The question is
This
how it will vary.
Yeah, I
What
think
is the term defining KD, or what's defining this?
actually That I don't know how they calculate KD, how they include KD, but I guess so.
I want to put a comment here that KD, QD are the parameters. Okay, I initially put from the beginning, and D actually depend upon the local environment. This root separation. Suppose suppose for water rigid model there is minus 0.8 charge. Okay, so I split it into root just for schematic example, minus 0.7 and minus 0.1. Okay, so there we means minus 0.1 if it is goes far means there is some strong interaction from the environment. This minus 1 part goes far apart. Okay, means makes the it mimics the electron density as this electron density means pulled out from that atom. Or if it is in other different kind other environment, then those are very close and it looks like that minus 0.8 charge. Okay, it is in concentrated region on oxygen. So D is the degrees of freedom determined by the environment, and depending upon this charge separation, okay, the local arrangement, all the local arrangement and structure are controlled. Means if there looks like a point charge, means root particle and the oxygen atom are in similar position, they acts like a point charge and control in that way. If there are very strong polarization effect, then they are very far apart and means this is huge polarizability. Then oxygen atom shows very huge polarizability, and in this way they affect the environment. So here degrees of freedom is D in the simulation.
Okay.
QD and KD are our parameters.
I get it once.
Okay.
Yeah, Subhajit, you may proceed.
Yeah.
Okay, so now the third one, basically the last one, that's fluctuating charge model. In this fluctuating charge model is something different. Like in this model, the polarizability is introduced in your standard potential energy function. Okay, so what I told initially, that's we modify this electrostatic interaction. We modify. So, and this standard energy function we modify by the coupling of this charge and the environment. Okay, so using some electronegative equalization. So this scheme is also called this uh, charge equalization scheme or fluctuating charge model. Okay, so in this methodology, like variable discrete charge are located on atomic sites or within a molecule. Okay, so the value is the electrostatic potential is computed for a given molecular geometry by the minimization of this electrostatic energy. So first I like to write this electrostatic energy function they have used for this fluctuating charge model. So this electrostatic is Q gives the charge, and write is a molecule, and alpha is the index of site. Okay. One term. Between different sites of an atom, oh sorry, of a molecule. There is a function of molecule, right? is for different molecule. Okay, so the notation is clear, but because this Q is your charge, okay, so this is charge of every atom, and the two thing, one is this Xi, and the another is a Z. So 0 is your molecular electronegativity, and this J 0, J you can say J is your absolute hardness. So this charge Py thus treated as independent variable, and the polarization response, you see that the polarization response is determined by the variation in the charges. So these charges are exactly depend on the interaction with the other molecule, as well as, so not on the interaction with the other molecule, as well as the other charges on the same molecule. So if you see this expression carefully, so then you can be able to see this interaction depends on with the interaction of other molecule as well as the charges of the same molecule, and it will change for every time step. So this is how they in this fluctuating charge model they taking this account this uh, the fluctuating charge which encounter this polarizability. So uh, now the again the same question comes, this fluctuating charge model is, like I already told, this root oscillator, classical root oscillator model is not that computationally cheaper with respect to this your induced dipole moment. But now the same question, the comparison comes, this FCM, like fluctuating charge model is computationally cheaper than this root oscillator model or not. In this regard, we can tell that a practical advantage of this approach is that it introduced polarizability within this new interaction without considering any extra charge interaction. But this fluctuating charge model is to capture the significant effect intermolecular interaction. You need this to this MD simulation, you need this shorter integration time step. So that again leading the computational cost high for this type of model. So none of these polarizable force field introduction method like induced dipole, root oscillator, fluctuating charge, none of these are computationally cheaper. So now the next question comes, like how one can implement this polarizability in computationally in a very efficient way. So as a recap, I can say like that the inclusion of polarizability increase the computational demand due to the addition of dipoles or additional charges center and the requirement of shorter integration time step in the context of MD simulation. So in addition, for every energy and force evolution, it's necessary to solve for all polarizable degrees of freedom in a self-consistent manner. So that's a huge computation. That's a huge. So traditionally, it is performed via self-consistent calculation, but self-consistent calculation until the induced polarization is converged to a particular value. The convergence is actually so it in so here the solution there is a solution for the implementation of this electronic polarizability in MD simulation. They are taking these polarizable degrees of freedom as dynamic variables, and this original idea is based on this Carr-Paradiddle approach. So in quantum mechanical simulation, which is your extended Lagrangian method. Obviously, it's a story for another Sunday. So that's all from my side. So thank you everyone for your attention. So if any one of you have any question, so I can try to answer. That's all from my side. Any question, Nivida?
Means here J0 is J, na? This J0,
J0 is
that's the diagonal term. Okay, this Mulliken electron term is more familiar than absolute hardness. So
absolute hardness.
How to calculate those absolute hardness parameter value means?
Yes. So this absolute hardness you can consider with this. This absolute hardness is defined as eta. So eta is equal to half of the second derivative of the ground state electronic energy with respect to the number of electrons. Okay, so in this consideration, you have to keep your nuclear charge, nuclear charge Z fixed. So this is how one can calculate this eta. So, but there is a Mulliken's expression, like as we know that this electronegativity in Mulliken, so we can calculate as a half of I plus A, whereas the ionization energy and the electron affinity A is. So in this context, we can calculate this absolute hardness eta as a half of I minus A. So you can calculate eta as this consideration as this, or you can calculate that is if you know this electronic ground state is a electronic ground state energy.
Okay. And here also this hard method, this fluctuating charge method, it is also done self-consistently on each nuclear environment. Okay, and second method, there is one thing is I think is missing, that main point, that why it is means it seems that there is only one root oscillator is needed, one extra variable is needed, so not much computational cost. Okay, if you compare the computational cost between this iterative method and this extra degrees of freedom root method, okay, so their computational cost is per therefore per sites there is those iteration. Okay, yes. Iteration means the same calculation again with the updated value. Okay, so number of iteration multiplied by this site, number of sites. Okay, so here in comparison to that, here one particle does not means it seems that it has much more efficient. It should be much more efficient. So,
but this extra charge calculation becomes problematic in terms of this computational cost.
Now in root we don't put any, those are parameters, and those basically solved by equation of motions. Okay, like extended Lagrangian for root here. So their extra another computational costly part comes from this time step. Okay, these for these degrees of freedom. Okay, so we have to choose the time step according to the time scale of this vibration of this root. This requires very small time step for root. So this is one more part for making it computationally costly. So just like
so typically
just like in CPMD there is okay, computationally costly part. It seems that Born-Oppenheimer dynamics from as compared to Born-Oppenheimer CPMD should be much more cheaper, but their computationally costly part comes from this time step, because these extra degrees of freedom for this electronic part, that natural vibration of electron is very fast. So that to capture this electronic sampling, we need to give very short time step. So here also, Subhajit, you are.
Yeah, just asking them what is the typical vibrational time scale of Drude oscillator? Like,
Drude oscillator,
yeah.
Drude has no mass, so I don't remember the number, but it should be order of faster. It's not like some greater than or less than, but order of faster. Order of magnitude faster.
Okay.
Just a query, like if a Drude oscillator is massless, so how do you define its kinetic energy?
Okay, Drude oscillator, it is a some kind of means we don't means there is no physical kinetic energy corresponding to the Drude oscillator. The whole means it is a means in it is defined in terms of extended Lagrangian form. Okay, there is some extra degrees of freedom, just like metadynamics. There is some auxiliary variable. Okay, in metadynamics, Shreya wrote that extended Lagrangian form. Okay, so in that auxiliary, for that auxiliary variable, there is no physical kinetic energy.
Okay. Okay.
So yes, there is no physical kinetic energy. No physical, that's why no physical mass of it.
And we are considering it as the spring only, so the potential energy form expression remains same as the harmonic oscillator.
Yeah, for Drude is the potential energy is harmonic oscillator, like, and it also for the Drude charge, there are others electrostatic potentials that depends on this electrostatic term, that depends on this position of the Drude. Yes, this QD. This position of
so this KD will be just since there is no mass, so generally we know it's like force constant is equals to m omega square. So here it's like directly just proportional to the omega square, that is the frequency of vibration. That's like
yeah, that you can think. Yes. Now frequency of vibration, no omega square means there you consider mass as 1. Means this KD is just means this is the only use to take it like oscillator, but you cannot translate it into other meaning of that oscillator. It has mass and frequency.
okay.
Means because
I will read about it a bit.
Yeah.
So there is one paper just I can say. You can read about the reference. This paper, they have first they've implement this. They've made this type of water model with this help of this classical.
Okay, you can share this paper. It would be better.
Okay.
In that group.
Ravi?
Yeah, I think it's in KD. So normally in force constant we use this reduced mass. So here mass will be of just that particle. Like if the root particle is near oxygen, then mass of oxygen is used.
Yeah, in that way we can understand the meaning of mass. Yes.
Yes. And yeah, very nice talk, Subhajit. Good.
For attention.
Thank you, Bansi. Actually, this question was in my mind. that how this druid is more computationally costly when we have single parameter.
Yes, this is only one degrees of freedom, but they are multiple iterative step. So
yes.
Just like these, when these Karp-Arinalo versus Born open dynamics will be discussed,
right?
Then I think the same problem means same kind of time scale issue will be discussed there.
ठीक है Subhajit.
And stop sharing.